Although it's not the most popular way to define a function, it is possible to define a function verbally. This becomes helpful in a few topics, most notably inverse functions. For now, we'll just mention that it is technically a definition of a function, right? For example, here we say the function complement takes as input the measure of an angle and subtracts it from 90 degrees. That is a definition of the function. Now that we have defined complement, we can refer to it. Remember, complement is the function name. 64 is in the position of the input, so that is suggesting that 64 is the input, and we will use this verbal definition to find the complement. Subtracting 64 from 90 means that we go in this direction, 90 minus 64, which gets us 26, and that would be our answer, right? So a verbal definition is perfectly legitimate. A symbolic function definition is what most of us picture when somebody says a function, right? When somebody refers to a function at all, we're probably most of the time thinking of a function that's defined symbolically, or that might be the first thing that comes to our mind. So that same function complement that we just defined verbally, we could define symbolically using a formula. To say that the input gets subtracted from 90 is the same as to say that the function is defined by the formula 90 minus x. So this is again calling the function complement with the input 88 to get this time a result of 2. If we take a more abstract example like this f of x equals negative 5x plus 1, we're now saying, okay, this negative 3 here is in the place of the input variable, which is x, and so the way I would evaluate this is to plug in this number for x. So this is going to be negative 5 times my input x plus 1, and I will put that input here, negative 3, in pink. And then all I need to do is evaluate. So we get positive 15 plus 1, which becomes 16. If I have a number as an input, I will generally have a number as an output. If, on the other hand, I have a variable expression as input, like for example x plus 3, then I should expect to have a variable expression as output, but the way that I get it is the same way that I got my output from the number. I still just plug this whole expression in for x. Note there's also a minus sign out front. I am going to work with that also. There's no way that I can bring that minus sign into the function. It is on the outside, and therefore I need to do this last. By order of operations, we can think of the function itself and its input as being a grouping, right? So we'll work with that that f of x plus 3 first. When we've got it resolved, we'll go ahead and distribute that minus in or do whatever it is we need to do with that. So I'll just trail it along for now and then worry about the f of x plus 3 in some brackets here to keep it separate. So again, the function f is negative 5 times its input plus 1. And its input this time is the whole expression x plus 3. So I now have a strictly algebraic expression to simplify. I'll start by distributing the negative 5 into the parentheses. So we're going to keep that green minus sign on the outside for now. This becomes negative 5x minus 15 plus 1. Now I can combine the minus 15 and the plus 1. Negative 5x minus 14. And finally, I'll go ahead and distribute that minus sign into the brackets, which will change the signs of both terms, giving me 5x plus 14. You can probably hear my foster cat meowing in the background. I don't know if you can hear that or not. I certainly can. So a function defined symbolically is not very different from an equation, right? If we think of the output as being the y variable and the input as being the x variable, then looking at this function defined by a formula, we could easily see that also as saying y is equal to negative 5x plus 1. And because of that, a symbolic relation is really just an equation in two variables. So we're going to look at these equations below, y equals 2x minus 3 and y equals plus or minus 3x. And we can see that the first one is a function and the second one is not a function. It's probably fairly obvious why that second one is not a function, right? This plus or minus symbol here generates two outputs. For example, if we just take x equals 1, right? We'll just take a super simple input and say, what is y? Well, y is positive 3 times 1, so y is positive 3. And y is negative 3 times 1, so y is negative 3. If we can do this with any of our inputs, then we have to say that it is not a function, right? It has violated the definition of a function. This first one is a function. We could imagine plugging in values of x and see if it's ever possible to get two values of y, and perhaps we would pretty quickly convince ourselves that it's not possible. But the key to identifying a function is that it is solved for y without a plus or minus symbol. Anything that is solved for y already is really well on its way to being proven a function, as long as it doesn't have a symbol like this that generates two outputs. So if it's solved for y, and there's no plus or minus, then we're in good shape. The bigger question is, what if it's not solved for y, right? And the answer to that is, well, it really could go either way. We will see this subject come up a little bit when we talk about solving quadratic equations, because we do introduce that plus or minus symbol sometimes when we're solving for y. But there are a lot of equations that can't even be solved for y, so it's not a question that can be answered in full generality at this stage. What we'll look for is equations that we can fairly simply solve for y, see if that process goes smoothly. And if we can do that without introducing a plus or minus symbol, then we can assume that it's a function. If a plus or minus symbol is already present or is introduced at any point along the way, then we would probably conclude that it is not a function. So with this next exercise, you might go ahead and pause the video and try it yourself. I'll work through these right now. The first one should be fairly obvious. Anytime we have this plus or minus symbol there, that's a pretty good indication that this is not a function. So this is no. If we want to be really sure, we could come up with an input that has more than one output, and it doesn't take long. Again, just start by trying 1, right? Let's see what happens if x is equal to 1. If x is equal to 1, y is 2 plus or minus 1. 2 plus 1 gets us 3. 2 minus 1 gets us 1. So we do, in fact, get two different outputs with that plus or minus. The second example here, y equals x squared minus 3, this one is often confused with the third example, which is x equals y squared. Remember, we said if it's solved for y without the use of a plus or minus symbol, then it's good to go. This one absolutely fits that description. So we can conclude that it's a function. It's the third one where when we start solving it for y, we have to introduce that plus or minus symbol. So when I solve this for y, I would take the plus or minus square root of both sides, and I really only have to put the plus or minus on one side, or else it becomes redundant. That becomes y equals plus or minus the square root of x. Again, that we do have that plus or minus, which introduces two outputs for one input. So this one we would say is not a function. Having the square on x doesn't make it violate the definition of a function. Having the square on y does, right? If we look back at this earlier example, this graph is a parabola. It's shifted down 3. We'll get into how to graph these in a few more chapters, but just to kind of put it in perspective, this is a parabola that opens up. This does not violate the vertical line test, right? Anywhere that I draw a vertical line, I can see that it really will only intersect the graph once. So having a square on x is no problem. Having a square on y is where we end up violating the definition of a function.